A radical function are functions that contain a radical. Wouldn't you know it? Now remember, the radical is this shape. Y'all have called it a square root for your whole life. It's called a root or a radical. And there are multiple kinds of roots depending on the little floaty number called an index that is on the ledge of the house there. Now there are two main radical functions that we're going to be talking about in this class. Those two are the square root function and the cube root function. There are higher order roots like fourth roots and fifth roots, but we're not really going to look at those in this class. We don't really even look at them until you get to maybe like higher level college classes. So these are the only two radical functions that we're going to be working with. Now, in a square root function, like every time we look at a function, there is a parent version of the function. So like the boring equation. For quadratics, it's x squared. For cubics, it's x cubed. So a square root function, the parent function, the one you probably need to try to remember, is f of x equal to square root of x. With no numbers, no, what are those things called? Negative signs, just a regular square root of x. That's the parent function for square roots. This square root function itself looks like this. Tell me some things you notice about the shape on the screen for the square root function. It's like a curve. What direction does it go? To the right. Does it make a full like U or C or anything like that? No. It's basically half of a parabola tilted on its side. And in true fashion, and if you ever take pre-cal, we'll talk about why it looks like this. But really, some important things to note is that the graph starts at 0, 0. So we're going to say it starts at 0, 0. That's super important to notice that it actually touches this coordinate point here called the origin, which means that the square root of 0 is 0. Fun fact. And then every single time you put an input in there, the output is the square root. So what is the square root of 1? 1. What is the square root of 4? 2. If we kept going and we went to square root of 9, it would be at 9, 3. So all of the inputs and outputs just take the square root of these numbers. Some important things to see about the domain and the range. The domain is talking about the x values, which means I'm looking at the values that the graph covers on the x-axis. Where does this graph start on the x-axis? What number? 0. So we're going to say that the domain starts at 0, and I'm using a bracket because it actually touches 0. Where does this graph end on the x-axis? Infinity. It doesn't end. It goes off screen to the right. So we'd say that the domain is from 0 to infinity. Another way this might be written, just depending on the type of answer that you're given, I like interval notation best, but you may also see this as x greater than or equal to 0, which is essentially saying all of the x values bigger than 0, which, yes, we are looking at the x values that are bigger than 0. So remember, domain is always the x values, which means range is the what? Y values. So if we look at the y-axis, where does the graph start on the y-axis? 0. And where does it end? Infinity. So the domain and the range are essentially the same. One is for x's and one is for y's, because we're trying to see where it shows up on the x-axis and on the y-axis. The other way you might see this written is as y greater than or equal to 0. One is called interval notation and one is called inequality notation. So if we look over here at the cube root function, it's completely different than the square root. I'm going to change colors again up here, so sorry. What do you notice about the cube root function's parent function? So I'm talking about this right here. What do you notice? It has the little 3, right? It's just a cube root of x. No extra numbers, no nothing. The only number showing in the parent function is the index. That index has to be there or else it is a square root function. Okay, so that's important to know the difference between cube root and square root. Now, what's the difference in the shape of the graph? It's like a sideways little squiggly, right? In fact, it is a cubic function, which looked like an S when we studied those, tilted on its side. And in pre-cal, we'll talk about why that happens, but here it don't really care. As long as you can recognize that the ones that go sideways, those are cube roots, we're in good shape. The thing I want you to think about, it's not really called the vertex, but this point right here, see how it's like the center of the squiggly line? It doesn't really have a name, so we're just going to call it the center of the graph for the parent function is at the coordinate point 0, 0. So just like the starting point of the square root, the center of the cube root is at the origin, 0, 0. And anytime we transform this graph, we're going to be moving that center as if it was the vertex of a parabola, but they're not. It's not called that. Now, if we look at the domain for this graph, if I look at the x-axis, where does this graph start? Negative infinity, because if I look, this graph goes off to the left and to the right. So how would I write the domain? Yes? Negative infinity that way, and what number that way? Positive infinity. Very good. Another way you might see this written is as all real numbers. Do y'all remember that symbol, the fun and funky R? That means all real numbers. Either way is appropriate. One is an interval notation, which I prefer, and the other one is called inequality notation. All real numbers. So that's a difference between these two graphs. One of them has a stopping point at 0, 0, or a starting point. The other of them goes on for forever. Now, this is a little bit confusing looking just because they're so flat. The range is actually also from negative infinity to positive infinity. And it's misleading when you look at the graph for this because of a few things. Number one, it looks like the way we have this graph that it's going to stop at -2. Do you agree? I also agree. Kind of looks like it's going to stop. And we'll learn more about these when we do another unit on rational functions, but that would mean that there's what's called a horizontal asymptote there. These functions do not have asymptotes at all. So we know that there is no stopping point, no boundary here. In fact, if we were to zoom out of this graph for forever, it's going to keep going out and down slowly but surely as we go out to infinity. Now, very slowly because it's pretty flat looking, but it is not exactly flat and it does not have an asymptote. So we know that that arrow is really actually going down just very, very slowly. So what you can remember here is that the cube root function is all real numbers for both answers literally every time you have a cube root. For both answers. Every single time, it's all real numbers for both. That is not the case for square root functions. That one is going to have a stopping and starting point on one of the sides. But the cube root functions, you should be excited when you see them because their domain and their range is easy. It's all real numbers for both every single time. Okay? Now, one of the things we're going to do with these functions, we're going to transform them. Now, this chart should look familiar to us. Have we seen this before? Yeah, literally every time we've studied a function, we have also transformed it. So we're going to go quickly through our transformations one more time so that you have this nice chart for yourself. If we are horizontally translating something, then we are just moving the graph either to the right or to the left. That number will be inside the radicand. It will be underneath the square root or the cube root. Whatever root you're taking, the plus or minus number that's underneath the radical is going to move my graph either to the right or to the left. So what's important for us to remember is that if you see a minus sign, that means the right. And if you see a plus sign, that means to the left. Those are some ugly looking minuses and pluses. Let me try that again. So on the inside, minus goes to the right, plus goes to the left. When that number is added and subtracted behind the radical, do you see the difference in the first row and the second row? How the number is inside versus outside? When it's outside, we are going either up or down. Plus is up, minus is down. Same rules as before. These rules have been the same every time you do a transformation. You have your reflections over the x and y axis. If the negative sign is in front of the entire radical, that's going to go over the x-axis. If the negative sign is underneath the radical in front of x, that's going to go over the y-axis. So by that I mean it's going to go from looking like, I can't do it with my arms. Here's my cubic function, and if it flips over the x-axis, it's going to do this. And if it flips over the y-axis, it's going to do this. So they end up looking the same, which is weird. But that's what we're flipping. We're picking the axis that we're flipping over. Now the last two are my vertical stretches and shrinks. We've seen these before. We remember that the horizontal ones are the weird ones. In fact, their number that you're multiplying by will be the number inside the radicand. So underneath the radical sign, or inside the square root or cube root, that's going to shift it, or going to wow, I used all the wrong words just then. It's going to either stretch it or shrink it horizontally. So you grab the edges of it and either stretch it or shrink it. Now, if you see a big number underneath the radical, it is called a shrink, and you have to flip the number. So instead of 3, we say 1/3. If the number underneath the radical is a fraction, it is called a stretch by its reciprocal. So the horizontal ones are the weird ones where you have to flip things around, but you just flip the number over. When that number is multiplied on the outside, however, it's much simpler. That big numbers are going to stretch it, and small numbers, aka true fractions, improper fractions, are stretches, shrink. It's going to shrink it by that exact number. So these are the same rules that have applied every time we've done transformations. Hopefully most of them are starting to look pretty familiar to us, or get familiar every time we go back over them. But you have this whole chart now of our transformations that matches up with the chart we've had for our polynomial functions, for our quadratic functions, for any of the functions that we studied in this class. In these practice problems, we are going to describe the transformation, graph the new function g of x, and then state the domain and range of the new function. So we're going to do 3 things each problem. The first thing we need to do is recognize what's different about the parent function and g of x. What do you notice is different? What has been added to g of x that was not in f of x? The -3 on the inside. Okay, what else? +4 on the outside. Cool. Now those are going to cause me to have transformations in this graph. If you want to flip your paper over and look at the chart again, what transformations are these called when you have a subtracting number on the inside and an adding number on the outside? The minus inside the radical, what is that going to do? Yeah, it's going to move it to the right. How many units? 3. And that +4 at the back, what is that going to do? Move it up how many? 4, but yeah, the number that is there. Cool. So we know that this has a horizontal translation to the right 3 and a vertical translation up 4, which means we are going to take the original parent function that is graphed on your paper, and we are going to actually shift it to the right 3 and up 4. Instead of starting the graph at 0, which is currently what's happening, we are going to start the graph by shifting it over 3 and up 4. That's where our graph is actually going to start, right here. Over 3, up 4. Did we do anything else to this function other than shift it? No. So when we graph this, we can plot the same points. Now the same points, the pattern for this, if you want to write it down, is over 1, up 1, over 4, up 2. So what I mean by that pattern is from our new starting point, we're going to go over 1 coordinate point and up 1 coordinate point and plot another point. Then we're going to go over from the starting point over 4. 1, 2, 3, 4, and we're going to go up 1, 2. Once you have those 3 points, you can play connect the dots, and you have your new graph. And if you're like, wait a second, that really just didn't click, the other option is to put this in your calculator and look at the table. It will give you the same coordinate points we just gave. 3, 4, 4, 5, and 7, 6. But the main idea here is that we have taken the shape and we have shifted it to the right 3 and up 4. Let's talk about the domain and range of this new graph. So the new one that we drew. If we look at the x's for the domain, where does this graph start on the x-axis? Oh, just the x value. What was it? 3. So we're going to start at 3 because we've shifted it to the right 3. Where does it stop? Infinity. So we're saying that our graph is taking up the x-axis from 3 out to infinity. That's our domain here. If we were using the inequality notation, that would be x greater than or equal to 3. Now don't move your paper. I'm going to flip mine back to the domain of the parent function. Leave yours on what you can see. We're going to talk about what has changed here. Now that we've made that connection into how it has changed from the parent function to this one, what do you think the range is going to change to? Instead of 0 to infinity, where does this graph start? Say again? 4. So we started our graph at 4, and then it goes off to infinity because there's no top of this graph. So we have 4, infinity. The inequality version of this, not x, is y greater than or equal to 4. Okay, cool. Now before we go to number 2, we're actually going to go to number 3 because it's the same type of function. So we can stick with these two for a second. If we look at, in number 3, the changes between the parent function of the square root and the g of x function, what things have changed? There's a negative, and then there's a 2. Okay, what else? And then the plus 1 on the inside. We just need to figure out what the name of those transformations are, but we can compare it to the chart. The green negative that's in front, look at your chart. Where else is there a negative in front of the whole thing? What is that called? Reflection, which axis? Reflection over the x. Cool, so we know that this is going to flip over. What else is it going to do? What does the big 2 in front do? Say again? Ooh, those will be numbers inside for the... A vertical stretch. Yeah, this is going to be a vertical stretch by a factor of 2. That means ours is going to get taller, essentially, because we're stretching it up. The plus 1 is on the inside. What does the plus 1 on the inside do? Moved it to the left how many units? 1. Okay, so we know the things we're going to do to this parent function. We're going to flip it over, we're going to stretch it out, and we're going to move it to the left. So let's do that. We're going to do this one a little less accurately. So if we know we're going to have to flip this over, should the shape exactly match this that's printed on your paper? Should be the same direction. No, what should it look like if it's reflected over the x? Like it's going down. Very good, because it's going to go from looking up to flipping over this axis, so it's going to go like this. We know that. Oh, that was a terrible, like this. We know that's going to happen, but we also know it's going to stretch out and move to the left. So let's go ahead and move it to the left, which means instead of starting at 0, what number are we going to start at? -1. So put yourself a starting point at -1. And because we're going to just do this one as a sketch and not an accurate graph, we're going to go ahead and make sure it goes the right direction and gets a little bit bigger than the other one. We're sketching this one instead of accurately graphing. But again, if you're asked to accurately graph, you can use your calculator to look at what it looks like, or Desmos to look at what it looks like if you're at home. But let's talk about the domain and range here, because we have a different looking graph than we did before. The domain is the x's, which means I'm looking to see where it starts on the x-axis. Where does it start on the x-axis? -1. Where does it end on the x-axis? Positive infinity. So we're going to say from -1 to positive infinity. Because again, all we changed was where it was starting on the x-axis, so we have to change that number. The inequality version of this would be x greater than or equal to -1. But the range is going to be different. Before, we had said, don't write this down, we had said the range was from 0 to positive infinity. But that's because the graph went up to positive infinity. Does our graph go up to positive infinity? No, it goes down. So a very tempting thing to do is to just do this. Why is that wrong? Because it's showing, I'm trying to say that it starts at 0 and ends down there at infinity, at negative infinity, right? But that's not the right way to write it for these y's. Can anybody tell me why? No, it isn't going straight down, you're right. That's not the reason. That's a good idea. So these are always done in number order. -1, isn't that smaller than infinity? But is 0 smaller than negative infinity? No, so what should I do with these two things to put them in the correct order? Negative infinity, comma 0. So we don't want to write it like that, although I know it is tempting. We actually want to put that smaller number first, which happens to be the negative infinity. And since I flipped the numbers in my inequality or interval notation, in inequality notation, I'm also going to flip-flop the sign, saying that all of the y values are less than or below 0. So if you have to flip-flop the numbers because of a reflection, you have to flip-flop the sign. That's why I personally think interval notation is easier, because you see both numbers. But that's my opinion as a mathematician. All right, well, there's our square roots. We're just taking that little curve and we're like moving it around the graph, maybe flipping it over and talking about the domain and range. We're going to do the same thing, but for this cubic function. This time, our parent function is cubic because I see the index of 3, but the transformations follow the same chart. What is this negative sign inside the radical going to do to my function? Reflect over the y-axis. Very good. We looked at our chart. We saw where that matched up on our chart. So we know it's going to flip-flop over the y-axis. Okay, noted. What else is going to happen? It's going to move up 5. Okay, so the moving up, like I said earlier, I mentioned earlier, is going to come not from the starting point anymore because these functions have extensions on both sides, but they're going to come from that center point. Okay, so let's start doing this. So we're going to take this shape, the squiggly line, and we're going to take the center away from 0, and where are we going to move the center? What does our transformation say to do to it? Move it up by what? 5. So we're going to go to 5, and we're going to put that new center point up there at 5. It also says that we need to reflect it over the y-axis. So everybody right now, I want you to just put an arrow at the y-axis so that you know which one you're going to flip it over. If you're going to take this shape that more or less looks like this with my arms and flip it over the y-axis, does it do this or does it do this? The first or the second one I just did. Which one is acting as the y-axis? Flipping it like this or flipping it like this? which one is the y-axis? The second one. So we don't want this graph to look like this. Don't draw this. That would be flipping over the x-axis. We actually want it to look like this. Flipping it over this y-axis. So there's our sketch. Again, if you're like, what, Ms. Quigley? You can always graph it on a graphing calculator or on Desmos to see what the shape looks like and sketch it on your paper. Now, these last two questions here should be like super easy. Because I told you earlier, the answer to domain and range for cube root functions is always the same. What's the domain? All real numbers. So we're going to write it in two ways. All real numbers in interval notation is from negative infinity to positive infinity. And in inequality notation, it's the fun and funky R. Now again, this next question should be really easy because it's the same every time it's cube root. What's the range? 5. Ooh, that's how much I moved it up.
Oh. It was like an infinity.
It's the infinities one again. Yeah, all real numbers from negative infinity to positive infinity, or the fun and funky R. Literally every time we do a cube root function, you're like, check, I got the domain and range because I can just copy paste this answer. It is always going to be all real numbers. If it's not, you drew it wrong. Okay, last problem here. Now here's a good question. I told you we'd be using radicals all day, and those are not radicals. Why is this still on these notes then? What could I do to make this look like a radical? It 100% would. If we remember numerator behind, denominator in front, isn't that just the cube root of x? And I can hide this one. So it's just the parent function. It's just written in exponent form. Okay, that's good to know. So in that case, how could I rewrite g of x so it actually looks like the cube root I've been working with? Cube root of x. Where does the plus 4 and minus 6 go? Which one's inside, which one's outside? 4 is on the inside, and the 6 is on the outside. How do you know the 4 is on the inside? Absolutely. It is in those parentheses. So if it's in the parentheses, it's in the radical. Okay? So don't let people trick you if they try to give these to you in exponent form. You know you can just flip-flop them around into radical form. Now, if this is the case, what does that number do to my radical function? And what does this number do to my radical function?
It goes to the right by 4.
Ooh, not the right.
No. Oh, it goes to the left by 4.
Left by 4
And then it goes down 6.
and down 6. Yeah, remember the inside and out, or the inside transformations are always backwards. So plus actually goes to the left and minus will go to the right. Well, that's easy because that only affects the center point, air quotes, or the starting point. So instead of having my starting point for this graph at 0, 0, where should I have my starting point?
No.
For sure, -6, so we know we're going down 6, but how much am I going to the left? 4. So here I am going to the left 4, and here I am going down 6. So I can put my actual starting point there. I've just taken the whole graph and I said moving to the left, moving down. Oh, sorry, left is this way for you. That was my left. Okay, and we're just going to do a sketch here again. So after you have your starting point, you're just going to give me the same squiggly because we didn't do anything to flip it around. Oh, that wasn't the best. Let's try that again. And as long as it looks like an elongated squiggly line, you've sketched the graph for me. Okay, now this should be a really straightforward answer. So I'm gonna call on some people. Brace yourself. Fabrizio, what is the domain of this? The negative infinity, comma, infinity. Or in other words, what does that R mean? All are real numbers. Very good. And again, this should be a straightforward answer. Corey, what's the range? So look at the one we did before this. The shape of the graph didn't really change at all, just the location. What was the range previously? Dude, look at your paper. Yeah. Oh, so this should also be what? All of the cube root functions are going to be all real numbers every single time. That should be a fun fact, just like math fact we know. Same as 2 + 2 is 4. Cube root functions are all real numbers for domain and range.